So, thank you very much. I'd like to start by very much thanking the organisers, all the effort that they put into organising these talks, and for the invite to come and speak to you all tonight. So, I'm going to be talking to you about Axion Dark Matter. This is sort of one of the things that is going off in research at the minute. And before we can really get into the meat of this talk, I'm going to have to explain the background. I'm not confident that you're all aware of what dark matter is. Certainly not what an axion is. I talk to many physicists that are hardcore and they have never come across one before. So I'll start with a little bit of the background. Now, the way that we understand our universe, we tend to observe it with telescopes. We have a nice look out, and what we see informs how we understand the universe and how our models progress and advance. Now, if something crops up that challenges one of these models, what tends to happen is somebody will come up with a theory and adjust what we currently understand and add and append to what we've got. So we'll come across this rather shortly, but this is how we're building up the idea of what dark matter might be. So let's start with trying to get an understanding of a bit more how we actually work out what matter's out there. How do we know what we're looking at? So what we do to measure the matter within galaxies, let's start with the obvious one. We look out there, and if it's emitting light, now light in this particular situation, we're not just talking about the visible stuff, we're talking about all of the electromagnetic radiation. So all the way from X-rays, gamma rays, all the way radio waves, microwaves, the entire lot, including the visible. So if it's emitting light, I'll keep referring to it as light, but just think every time I say light, I actually probably mean full spectrum radiation. So anything that's emitting light, well, that's quite an easy one. We just look at it and we say, right, we've got an idea of what that is. Excellent. What about if something, for example, that doesn't emit light? How would we detect a planet per se? Well, if it happens to pass between the light source, the star, and us, well, what we tend to do there is to look for the brightness of how bright this star was, and when something passes across the front of it, it casts a shadow. So in casting this shadow, we then get an indication of how big it is, how frequently it casts the shadow, gives us an idea of how far out from this particular star this object is. This has been very successful for us in recent years. I mean, you might have heard in the news, probably 3 or 4 years ago now, thinking about it, that makes me feel old, that we were discovering a hell of a lot of planets, and there's quite a lot that are similar to Earth that we were particularly looking for, but that was more of the ones that were chosen out of the specific case. So yeah, we've got now an idea of things that are emitting light and planets that are orbiting these things emitting light for the most part. Well, there's another couple of methods, and this is where we get into the slightly more hardcore physics. So, according to Einstein's theory of general relativity, yeah, exactly, I'm already hitting that one hard, gravity warps both space and time. This also means it's capable of bending light. So if we had an object heavy enough, so let's say a cluster of galaxies that are relatively close in terms of space terms, then these are capable of bending the light of an object coming from behind them. So just like we see up here, this object behind, ordinarily we wouldn't be able to see it. It's directly behind this galaxy cluster. Well, because it's such heavy galaxy cluster, it bends the light around and we can see it. Now, because we know how this works and we can get a measure of various things, such as how far apart we're seeing multiple copies of things and various other methods, such as knowing how far away this particular small galaxy in the background is, due to various things like redshifting and the standard ways we would measure that sort of thing, we can actually get an indication for how much mass we would expect this particular galaxy cluster to have housed within it. So there's another way that we can say, right, okay, the matter that's out there. So, fantastic. Now, dialing it back a little bit into a bit more of an older physics, Newtonian mechanics. So, if we were to map out all of the things that we can now detect within a galaxy, so we know where the planets are, we know where all the stars are, very often gas will emit radiation such as X-rays, or it might absorb various bits coming from other objects such as stars. Well, we can map this out, and what we would expect is to see something like this disk line just here, and that's decaying off at 1 over the square root of r, which is not what we see. The actual data from this particular one is this line here. Coming out of the galactic centre, it's actually quite flat, which poses a problem because knowing that gravity is what's holding everything in and stopping it from flying off into space, things shouldn't be able to move quite so quickly. Now, if an object is moving at a certain rate when it's held in by a known amount of force, we should be able to calculate what that speed is. Well, these rotation speeds are suggesting otherwise, suggesting to us we have more mass within that particular galaxy than what we can detect with our conventional methods, or potentially with our conventional known about forms of matter. And so, I put one up there. You might be a little bit concerned, oh, he's picked one of those particular special cases there just to prove a point. Nope, there we go, there's a load more. We're not short of things that follow the same trend. So that's a good cause to believe that we're missing something. Now, it's not the only way. So if we have two galaxies colliding, for example, if they're big enough to cause gravitational lensing, which is what we're actually seeing over these sides here, in the blue, / purpley sort of colour, then we can say that once these two galaxies have passed through each other, the amount of matter that has collided, has actually interacted, it's very unlikely to be stars and things, they're quite sparse, but a lot of things that you would potentially assume might make up a large bulk of mass, so gases within galaxies. Now these are almost certainly going to collide, so luckily when they do, they actually tend to collide and emit radiation. Now that's what this blob in the middle is. The collisional gases have emitted X-rays and we have detected them. And you can see from the various issues with the way that things are starting to look, well, the majority of the matter that's there hasn't actually interacted at all, which means all of this other stuff that we're starting to think, oh, well, maybe it could have just been gases in the galaxies more so than what we thought. Well, the gas has just collided itself out, and it's still, the mass is still concentrated around the galaxy. So this other stuff, as we're currently calling it, is not interacting very well. And then we come on to one of the big killer sources, which is the cosmic microwave background. Now, I'm not going to explain this in too much detail, but for anybody who has heard about it before or has heard about the dark matter problem before, this is more of an interesting point. So this cosmic microwave background, as we're calling it, it's microwaves now, it certainly wasn't when it first started being. Now, it can be thought of as a snapshot of the radiation in the universe at a time somewhere in the region of about 300,000 years after the Big Bang. Now, were much, 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 much further beyond the Big Bang at this stage. So this light was particularly sort of emitted / allowed to be released when the universe was first starting to become transparent. So it's first starting to allow photons to pass through it without immediately blocking them. So it gives us a good idea of what might have been going off. Now, this is where it gets really complicated, and I don't want any questions on this particular bit, because the words that are about to come out of my mouth won't make a lot of sense. What we do is a multi-parameter cosmological fit of the background fluctuations. Yep, exactly. But basically what this boils down to is we've fitted some simulation to it essentially, and the parameters that's fallen out give us an idea of how much matter is within the universe. So we've got baryonic matter, the same stuff that you, I, and stars and planets are made out of. About 5%. Dark matter, 20 to 25%. Now, we still don't know what this dark matter is yet, but we'll come on to that in just a minute. And then the other 75 being quintessence / dark energy, and way more mysterious, way beyond the scope of this talk and my knowledge and understanding of everything. So, I alluded to it already, what is this dark matter? Now, there's multiple candidates, as we like to call them. It's just possibilities of what these things could be. WIMPs, weakly interacting massive particles. They're about the sort of mass of a heavy nucleus. Mass WZ boson, electroweak physics, where they originate. You'd fit somewhere in the region of about 100 of them in a pint glass. That's sort of the amount of a nice measure. You can sort of imagine a pint glass. There's 100 in there. Then we've got axions, this one that I'm actually here to talk about. Now this comes from quantum chromodynamics, which is rather complicated theory, which again, beyond the scope of the talk, more so because I would send myself to sleep trying to talk about it. Unknown mass, but it's certainly much, much, much lighter than WIMPs. Now we're talking electron volt absolute tops, so this is something that's less than the mass of an electron. We get about 10 to the 15 of these in a pint glass. Yeah, that one's a bit trickier to comprehend. 10 to the 15 is a huge, huge number. So, you might have noticed this blue bit at the bottom. I've not mentioned any similarities yet, have I? So, there is some big, big differences there. Similarities, now, they must all be very long-lived and not very prone to decaying. And these things are supposed to have come from the dawn of the universe very soon after the Big Bang. Well, they're still here today, which means they've not decayed and gone away. They're both something that doesn't come as a solution to the dark matter problem. They have both come from other areas of physics, which we have gained an understanding of through our observations and through the theories and the advancement of the theories. Neither of them have we yet proven. So, now we're getting into the really hardcore stuff, I'm afraid, for just a short while. Where does this axion come from? Well, this is what we call the strong CP problem, and is some quite tricky maths, is ultimately where it falls out from, and some very tricky to understand theories, but I am going to do my best with a couple of analogies thrown in there to try and get this point generally across. So what we have is C, or charge conjugation. There's a tricky one. So imagine this here is a helium atom. No, it's not, it's hydrogen. It's definitely hydrogen. Sorry, I've got helium on the brain at the minute. We've been having a lot of conversations about it at work. What would happen if we were to mirror this by charge? So charge conjugation is what would happen in terms of the physics if we were to flip the charges. Well, in this particular case, our physics should still be relatively valid. We've still got something which we can understand the model of. P, or parity, is another one. So parity inversion, what happens if we mirror it? So this pool table here, what happens if we mirror the physical pool table with all of its velocities and all of its positions? Just take the negative of those. Well, as you can probably see there, it's still a pool table, the balls are just set up slightly wrong. So it, again, pretty much works. Physics is not suddenly broken. Now if we have both of these, so what we call CP, what we would expect from our observations in physics is that under weak interactions, these are almost but not quite conserved, and that's absolutely fine. We've not got a problem with that until we come across strong force interactions. Then it's almost exactly conserved, which poses us a couple of problems, because for CP to be almost exactly conserved when there's nothing in our theory at all, there's nothing in the maths that would suggest it's supposed to be. Now either we've got something wrong in the maths, which of course highly possible, or something a bit strange is going off with the universe. Now, in order to try and explain how we solve this is even more complex theory that I won't claim to understand. However, two very, very good theoretical physicists, Robert Peccei and Helen Quinn, in the 1970s and late 70s, they came up with this solution to what we're calling the strong CP problem. So the strong CP problem, just a quick reminder, is this. It's when we have CP, it's not conserved in weak interaction, it is conserved in strong interaction, but there's no reason it should be conserved. Now this is the problem that we're trying to solve. Very, 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 very difficult physics to try and explain even to an experimentalist, which I am. And luckily, we've got a saving grace here. P.S. Keele came up with a very nice analogy. Now it's flawed in a couple of ways, however it will help me here to explain how this, what we call the Peccei-Quinn mechanism, fixes strong CP. So we start by considering a snooker ball on a flat table. Excuse me for a second. Now, if we move this snooker ball to any position on this table, so long as it remains within the confines of this table, our physics is still valid. Now this is what we call translational symmetry. It's very much what we were discussing, similar enough to what we're discussing with the CP. If we start changing certain things, the physics works the same. Our nice flat table. So, what happens if you stand on the table and you look over the edge? Well, what if we see a rather jaggedy, horrible looking landscape like this? Well, what if this is the natural way that things should be, and our artificially flat table is, yes, it's what we're observing, however, it's not the natural state of being. It's somehow become flat when everything around it isn't. Now, this is one thing that we could pose is, imagine this ball here is a theorist, because nobody else is going to actually wants to try and tackle this problem. Standing on that table, I can see over the edge, I can see it's not quite right, things aren't adding up. Problem is, I can't see through the table. I don't know what's happening underneath it. So let's imagine initially, oh, it's got legs, it's fine. We'll adjust the legs until the table is flat again. Well, this is what we call a fine-tuning problem, and is something that we tend to try and avoid. Now, we tend to try and avoid fine-tuning problems because the probability of it coming about all on its own is rather unlikely. If you think about the various number of different possibilities of things that have to combine in a very set way in order to get this table to be flat, well, it's going to be a rather tricky one, and so we'd like to have a model that fixes it all on its own without having to deal with these legs of infinite variability. So what we do is we come up with a mechanism to do it. Now we insert a hinge and a bar and a counterweight. Now this table is now self-leveled. So this mechanism now still has our flat table. However, underneath it we've now got a couple less parameters. We've got how far away the hinge is, how heavy the counterweight is, how long the arm is. Much easier. So this is quite a good analogy for what we think we're seeing and how the Pechiquin mechanism actually comes about fixing this strong CP problem I keep going on about. Arbitrary angle of the table, early universe, when all of this stuff we're talking about still wasn't valid. We're still not gone to the inflation point. Things are still incredibly hot, sea of plasma, very, very early on. Now, the table's just swinging round, it's doing whatever it wants. CP is still broken. Then the levelling mechanism kicks in as things start to expand and cool, and what we get at late times, low energies, is this mechanism is now functional. It's working. The table is level, we're on the table, nothing seems wrong. So that's what the Pechiquin mechanism is. So this later time that we're currently in is very much active. The mechanism is active. Now, you might say, well, the table can still rock from side to side. Very true. That's where axions come about, because these little wobbles in this table can be thought of as a good analogy for where the axion actually pops back into our usable physics. And these are through its interactions and its what we call couplings. Now, these are very weak, and what we have here, the axion over on this left-hand side, these are Feynman diagrams. And here we've got some quarks. This one, we've got the axion coming in, and to some fermions, so the electron, for example. And then we have the other one. Now this is the big one that I'm going to circle for quite a while, because this is the one that we try to utilise in order to try and find these axions. And this is the axion to photon coupling. So photons are the carrier of the electromagnetic force / radiation that we have already discussed tonight in how we look out at a galaxy. These are all photons. Radio waves are carried by photons. All gets into sort of the wave-particle duality sort of nature of things that I'm not covering in this talk. But what we have is these values here are an indicator of how strongly this axion is going to couple / convert into these other things. This is the one that we're interested in, mainly. So we look, and these couplings, what it turns out is actually very much dependent on the mass of the axion. So I've already mentioned it might be dark matter, or inherent property of dark matter is it has a mass. Well, I've also mentioned that we don't know what the mass of the axion is. If we knew what the mass of the axion is, I think we might have found it by now. So what we have to rely on is that these couplings, so how strongly it interacts with things, are proportional to that mass. We also, turns out that a lot of its other properties, so how many of them there are, that 10 to the 15 in a pint glass I gave you, is actually very much dependent on the mass of the axion. Inversely proportional, albeit, so the heavier the axion is, the less of them there are, the lighter it is, the more of them there are. And it's also very much indicative, again, inversely proportional, as to how early these axions were created. Created earlier, lighter, harder to detect, but there's more of them. Yeah, so it gets a little bit complicated, but we have somewhat abilities to guess and or work out what this axion mass actually is. Now what we've got here is a plot, the horizontal plot of the axion mass along this end, bottom side. This one up here you haven't got to worry about, that's all to do with this number just here. But what we can do is say that, right, okay, because we know that how strongly it couples is proportional to its mass, if it gets beyond a certain point, it will then be interacting with things that we have already observed, things that we already know how they are working and how they should work. Now, that would be all these things. Because we've not detected any of them yet, we can be pretty sure that it's not interacted up here, so it's all excluded. We don't need to look up here. All we have to do is look in this region, all the way down here. And so, when we come to actually looking at this region down here, how might we go about doing that? Now again, I'm going to loop back round, mention that axion to photon thing again, and also the fact that the electromagnetic forces are conveyed by photons. So we set up a magnetic field, and what actually happens there is we have some photons that are, okay, virtual photons because they never actually pop into being in the same way as what we would be able to detect them, but they are the magnetic field. And so if this axion comes across a magnetic field, it no longer has to create two photons from itself. One of the photons can already exist because of this magnetic field. So what we do is we then utilise the fact that that magnetic field's there, and all of a sudden the axion has a route to be able to convert into another photon, so we get a photon popping out. What do we do with the photon? Well, it's not quite as easy as looking for it because of the numbers of them that we're expecting. It's rather low. So what we have to do is we have to use what we call a resonant structure. Now this is something that can best be described as probably a can. Now if we imagine it's a rather large can, but it's usually some sort of empty, hollow metal box. Now in the same sort of way as what a guitar string has a natural frequency that it resonates at based on its length, well, a cavity will have a natural frequency, or actually quite a complicated set of, that it wants to resonate at, all based upon its dimensions, usually. So what can we do about that? Well, it's got a couple that it likes to resonate at. Well, we don't just want one. As I've mentioned, we don't know what the mass of this axion is. We don't know what frequency it's going to pop up at. So what we have to do is tune it. So we stick another rod in there and then we move it round. And what that does is probably best described by what happens if you put your finger on a guitar string to block its position off. You change its frequency. And there is only a certain range in which you can change that frequency. But we then get something where we have some sort of axion coming into. Now how do we get it back out again? Well, we stick an antenna in there and hook a radio up to it, is what that boils down to. So I'm going to take a small sidestep here into this logo that you've seen up in the top left corner. Now this is going to become sort of abundantly clear in a second as to why I've taken a sidestep. But the quantum sensors for the hidden sector group is the one that I am currently part of. The one that my supervisor started a couple of years ago, and it's a collaboration between 8 institutes, and we have an American collaborator, which is called Axion Dark Matter Experiment, or ADMX. I will be referring to them as ADMX because Axion Dark Matter Experiment is a bit too much of a mouthful to keep repeating, and I will, unfortunately for you lot, keep repeating it. So, what are we doing? Well, we're trying to build one of these detectors, and we've got funding for it, we've got equipment coming. I'll dial down a little bit more into some of that in a short while. But first, back onto ADMX. Now, you see why I've taken that segue to explain who's who and what's what. This is ADMX's very early generation cavity, and as we can see here, this is an actual photo with the lid off of one of these cavities that I've been talking about. So we've got the tuning rods in there. Yes, we've now gone to 2 rather than 1 because we get slightly more tuning range and slightly more adjustability out of it. It's 1 metre deep, 50 centimetres wide, and that bit of radio that I was talking about, well, it's not just a transistor radio. It's actually quite a very complicated setup that comes through this chain just here with various bits of amplifier technology and cooling technology and things like that, which will all, I assure you, make some more sense in a bit if you stick with me. But you might ask, how much power are we expecting from this thing? We're tuning a radio to it. We're expecting to hear some sort of hum coming off this radio. Well, how much? Just how much are we actually going to have to try and find? Well, there we go, maths. We've got a nice equation there for the power. Now this one has been normalised to the ADMX cavity, so what I actually have here, we've got the wrong version of the presentation. This B is our magnetic field. So we notice that's the square of that. So if we have a really strong magnetic field, we can promote this conversion to the photon a lot more, giving us more power. If we have a large volume, again, more power. And it's very much dependent on the frequency, which I alluded to earlier. This coupling being proportional to its mass, well, how much power we're getting out, if it's coupling more strongly, we've got a higher frequency. That is the same relationship. So, now we've covered bits of this, we'll put the numbers in for ADMX, which actually turns all of these brackets here into 1s, and we get 10 to the minus 21 watts. 10 to the minus 21 watts isn't a lot at all, but you might think, oh, it's fine, I'm sure we can amplify that up, just stick it into that old amp that we've got. Yeah, so what we have to count for then is how much background noise have we got. Well, this all tends in our particular case to come from what we call Johnson noise. And this is essentially electrons jiggling round, emitting radiation, and they do that quite consistently at all frequencies. So what we then do is we go about calculating how much power we're getting out of this noise. And plug some numbers in, we get this formula here, and this just a constant. This is the temperature. Now, temperature in Kelvin, science, use Kelvin, much better. And then B, which is the bandwidth. Yeah, I know, there's multiple B's in this thing if we actually look through it too quickly. It confuses me on a daily basis, but unfortunately, I'm not high enough up to make changes to adjust what letters we're using. This particular B is what we call the bandwidth. So how many frequencies are we looking at all at once? Well, again, tricky-ish sort of question to answer, but this is all stemming from the fact that the electrons are emitting just as much, and all this Johnson noise is created just as much at all frequencies. hence the reason we have this multiplier on there. And we plug the numbers in for actually quite an early ADMX experiment. They've gone down in temperature now. And we get 4 times 10 to the minus 20 watts. Just going to jump back a slide there. Minus 21. 10 to the minus 21 there, 10 to the minus 20 there. 40 to 50 times the power from the noise that we are getting coming from the signal. Well, multiple things we can do about that, but that gets into really complicated stuff that would probably take me an additional hour to manage to run through it all and explain it. What it boils down to is we sit there and listen for longer. What happens with noise is as the noise jiggles round randomly, taking averages can reduce the amount of noise because one noise point might offset another. Eventually you get a signal popping out the other end. So currently, mentioned that temperature, big factor. So we run as cold as possible. Now that's what this sort of thing is here. This is ADMX's current setup. What we've got here is the magnet. And everything else is all to do with keeping it very, very, very cold. Pouring liquid helium on. Pouring liquid nitrogen into one of the layers. Various things like this. Now, problems with running very cold. There's quite a few of them. Side note, that's me working on it when I went over to Seattle in the US. Oh dear, years ago. In practice, we've got problems. Got quite a few problems actually. So I mentioned that these cavities have lots of natural frequencies that they like to sing at. Well, each one of those frequencies is what we call a mode. And there's only one of them we can use. The rest are ineffective for our purposes. So, bit of an issue, we're actually only using one of them. It has some other slight side effects as well that is quite a complicated one to get your head around. However, what we can boil it down to is the mode of a cavity doesn't actually necessarily take up the entirety of the cavity in one clean direction. And all we're interested in is the overlap between this cavity mode and the magnetic field. Now when we overlap these, we actually get figures out with tuning rods in place of around 0.35. What that actually means is 35% of our volume is the actual effective volume that's useful to us. The other 65% is completely wasted space. Hence the reason we'd like to not just be able to use one. If we could use more than one, or if we could use a different structure that allowed for a larger fraction of that used, we get more power out, which means we've got more chance of detecting it in the first place. Then we've got to dwell at a sufficiently long time. This is all this averaging stuff I mentioned. And I also mentioned we're running very, very cold. Now, at 150 millikelvin, which is what ADMX is currently running at, everything is solid. Everything. Which also means if you try and move a tuning rod round in it, it wants to seize up on you. Which poses quite a few problems for being able to tune the thing. And then, due to the way that these resonances are created and how the structure creates this electromagnetic form inside of the cavity, we can only tune it by about plus or minus 15% by moving these rods round. Then what we have to do is we have to take it apart, take everything, warm everything up, and swap the physical cavity for something of a different size. Now this is usually, in our particular case, reduce the diameter of the bore. And then add more of them that all look the same to keep the same volume, because again, all the way back here, volume is a big factor. So, can we do something different? Nah, joking. We're not getting to that yet. what we've currently got, it does work. We're getting somewhere. Now, this is ADMX. These ones that are plunging down deeper are its current generation. These ones that aren't quite so deep are its previous generation. This one is one of the pilot experiments. Rochester, Brookhaven, Fermilab. Again, very much similar setups. They're all basically the same sort of thing, which is what we call a cavity haloscope. Not going to bother explaining that one. I haven't got the time. It will take too long. But a couple of notable things on here. Now, the horizontal axis is the frequency or the mass. It's both. They are directly proportional to each other. This one is all to do with how strongly we've managed to get down to our coupling. Now, this big band through here is where we think, due to various different models, where the axion might exist. So we have to plunge down into this, preferably as far down into it as we possibly can, in order to have any chance of detecting the axion. Now, an axion search is a bit like what you do when you've lost your keys. You run around in a blind panic all over the place until you've either found them or excluded a particular location from their existence. Yeah, that's what we're doing. We are literally just scanning through, looking at every possible place we can until we've checked everywhere, and if we don't find them, then we tell the theorists they must have been wrong, or they have come up with a better idea of where we should be looking in the meantime. There is something that we can do, potentially, but it's going to have to take a little step back into how these cavities get these resonances. Sorry, I do realise that I'm looping over myself a few times here, but I'm trying to link it together without speeding off at a rate that I would have completed this talk 20 minutes ago. So, the way that we can think of a cavity getting its resonances. Now, it's metal-walled, empty metal-walled box, and these natural resonances are created by the cavity's walls. The cavity's walls is what's giving them their resonances. Right, let's strip the walls away. They're a nuisance. Suddenly we've got a top and a bottom. Top and a bottom. But of course, that's not just going to resonate all on its own. It's not going to sit there and sing to you. So we have to still connect them in some way. So we connect them with wires. Again, connecting this all up with wires is not going to sing. It's not going to give us these resonances. Now, that just means we stick something in it. Now, this something is, excuse me, is almost the entire structure that we're after. It can be an actual physical circuit. It can be made up of capacitors and inductors, which will resonate. These structures will resonate if you wire them up in the right way. But the problem with that is once you've wired it up, it's sort of a bit stuck at that one frequency. So we're back to the old problem of this particular cavity not being tunable, because we've not got any way of tuning it. So what do? Let's go down the digital route. Everything's digital these days, so that's what we do. Use an analog to digital converter. So we've got a voltage signal on this end, that's coming from up here, and then we do our digital filter circuit. So what we now do is we add some parameters in, and it spits out the appropriate looking structure. And then we convert it back from digital to analog, and digital to analog converter, or DAC, and then we, again, back to here, stick it in the other side. And all of a sudden we've got this. Now, this has got advantages, big advantages. This form factor thing I was mentioning, so how much of the volume is effectively usable. Well, we can design around that now, because we're no longer being forced to use a structure that actually has something doesn't have to have multiple modes. We're in full control of this now. So, we're good there. Mechanical tuning, mentioned everything seizes up. Well, no longer. Things don't seize up when you're just punching numbers into a keyboard and it updates everything digitally, which is sometimes an issue. Tuning range, this 10-15% I mentioned, plus minus, well, that's gone away as well because now we're creating it artificially. We just sit it wherever we want, so long as it doesn't interfere with whatever the natural structure has. And then there's the big clincher. Previously, up to now, what we're doing, we're always looking in just one place at once. We're looking at this one frequency, then we're tuning and looking at the next one. Tuning and looking at the next one. And so on, and so on, until we've found everywhere. Not anymore, we're creating it digitally, we can put multiples in there all at once. But, when I say digitally, there's a slight snag. I'm actually not just a PhD student at the University of Sheffield, I'm also a computer systems administrator. And I know for a fact, computers do not do what they are told. They are so easily distracted, ooh, shiny, that you can't get them to do this kind of application. They just will not do it. If you was to walk up to the computer that's running this application and touch its keyboard, touch its mouse, it'll immediately start listening to the keyboard or the mouse and not running this particular filter, which we really need to run all the time. So what do? Field programmable gate arrays, logic circuits. Let's use ands, nots, ors, and all of that nice stuff that can't really be interrupted much, purely on the basis of it sits there and does exactly as you told it all the time. So here's a couple of them that I've been using, and this is one that features prominently over the next couple of slides. This is what we're aiming to try and use in the next, well, hopefully a couple of months, we'll see. And this is a hell of a lot more expensive and nicer bit of kit that maybe we'll get round to using if we can get the easier ones working. And this is the one that I created. Now this is not through any sort of other structure, this is just the digital filter. But, as you can see, I've now got 8 peaks. Those 8 peaks are potentially all going to be put into the same physical structure and are all simultaneously an Axion detector. We've just sped up the search by a factor of 8. So hopefully, this being $80 worth of equipment, the couple of grand's worth, we can fit 100 on. So we're getting there with what we might actually be able to improve things as. So we went and tested things. Now, got a collaborator over at ADMX who was very kind and tested this for us on a warm cavity. Can't quite justify putting it all the way down to 150 millikelvin until we've tested it works at room. So we wire this up like this. This is actually that blue board that I mentioned earlier. And as you can see, it's a rather basic prototype type system. This is strip board that we have to do some pre-processing on first. That's just an analog circuit that we've made as a quick and dirty way of making things work for the prototype. You might notice that says 110 volts. Yep, whenever you take anything over to the States, you aren't going to find any equipment in the lab that you go to. Just take it with you, it's far easier. Now, the more observant amongst you may have noticed that looks rather like a cavity. Yeah. So, remember that thing I was talking about before with all of the noise? Well, these devices are particularly susceptible to noise outside of the range, so all the way over here and all the way over there, where we are interested. Cavities, because of this natural mode structure, act as very, very good filters. They just drop off all of that stuff to the sides. So we go back to using a cavity for a little while we design this better structure, and so we can understand the technology that we're working with and how much we can achieve with it. And here's some data. We've got, the light blue on there is 4 resonators. Potentially, drop that down to cryogenic temperatures, it's already a detector. Oh, we did that. It was working, so drop it down. ADMX has this tiny little cavity that they use called sidecar. It operates at 150 millikelvin. So, sorry, I've not clarified that one yet. Minus 273 degrees Celsius. Gold. And it does operate within a little bit of a magnetic field, but it's only the stray field from the main cavity. So where I was working before in that picture is actually off to this side here. The big cavity that sits between the magnets is actually sitting down just below. It operates in a little bit of a field, but it would never be enough to actually detect axions. It's not strong enough at that. Nor is there enough volume to get the sufficient power out of it, because again, this is rather small. But, again, more data. We can see it worked. We can see these structures. Now, these are the ones that we artificially created, all of these, all peeking out from the noise. Now, that's all well and good. But I did say I was going to sort of loop back round to this QSHS and what we're trying to do. Well, we've got a system on order that will take us down to 10 millikelvin. It's minus 273.14 degrees Celsius. If you get any colder, we think physics breaks to an extent. If you get all the way down to 0 Kelvin, in theory, things have no energy at all. Now, we're speccing this system and having it built, and it's still not here yet because we've only just placed the order for it. So we're waiting till about mid-June, I think. And with any luck, that'll turn up, we'll install some equipment in it, and we get to test all of this stuff for ourselves on an even colder system. But of course, we're talking about such low power levels. Now, the majority of our groups in QSHS, quantum sensors for the hidden sector, what they're actually doing, the majority of our groups, is creating amplifiers, quantum limited amplifiers. So we're already getting down to the state where we'd be touching on the standard quantum limit, which again is a talk of its own. Unfortunately, there's a lot of these things in the field I work in, and so any talk I give, I'm going to have to brush over the odd few little bits. But what we've got is various groups doing various things. We've got some creating qubits, which can be used as photon counters. So in actual fact, one way of getting around a quantum limit is to be able to just measure the numbers of photons. If we try measuring the phase of them or any other property of them, we're suddenly not working anymore, we're back above the quantum limit. But if we just measure numbers, the standard quantum limit and all of the noise and things does not quite apply. Johnson noise still applies, but again, running cold. We've got Josephson parametric amplifiers, I believe those ones are. We've got squids, we've got kinetic inductance amplifiers, all of which I'm not an expert on, so I'm not going to try and explain to you. But there we go, that's what our group is mostly doing. And we're trying to apply these devices specifically for the case of Axion searches and dark matter searching. So, in summary, hopefully I've not taken up too much of your time, or for that matter sent anybody to sleep. But the universe is more dark matter than it is ordinary matter. We still don't know what this dark matter is. Now, we've got a couple of ideas. Could be these WIMPs. I'll slag those off in another talk. It's all right, I get to say that. My girlfriend's a WIMP searcher. But it could be axions, and I'm of a firm believer that we actually could have both. There's nothing excluding them from coexisting. So long as we all keep looking, we all keep friends. Let the high-ups and all of the professors argue about who gets what money. Currently searching for axions, aid their conversion using a magnetic field into photons. We capture those photons and we look for that tiny little bit of power coming out the other end with a cavity. It's effective, it does work, but unfortunately, given the various parameters it operates under, it has its issues, very well known issues. And so we think we might be able to improve it, try and wipe out the majority of these issues by using these digital logic circuits, FPGAs. And we're looking in multiple places simultaneously. If we can look in 100 places simultaneously, the current predicted scan range of ADMX could be covered in about 50 days. It's currently predicted to take over 20 years. Just flicking back quickly, that lot is about 30 years worth of data, if not a little bit more. So, if we can speed that up so that we've covered it all again and most of the other stuff around it, in 50 days we're doing pretty well and we might stand a chance of finding something. And rounding it off, QSHS collaboration in the UK, we are looking to implement quantum electronics. We're looking to try and implement some of these very novel but hopefully very successful techniques to actually find what dark matter is. Thank you very much, everybody.